Alright gang, here we go. This is for Chem 2 Unit 11, talking about factors that affect acid strength. Alright, so the whole point of this is that you'd be able to look at a list of acids and be able to figure out, well, which one would be the strongest based on these properties that we know. Alright, so it's kind of like periodic trends, alright, but we're looking at acid trends. Alright, so it's factor number one, that HA bond must be polarized with a partial positive on the hydrogen atom and a partial negative on the anion, okay, or whatever your A atom is. So this really applies best in binary elements, but this also kind of works when you're looking at other things. The more polar of the bond this is, the more likely it is you're going to have a stronger acid. Number two, your bond strength. The weaker the bonds between that hydrogen and whatever your other element is, all right, the stronger the acid will be. Okay, so because that means that bond can be broken easier, and therefore that hydrogen will come off quicker. Last one here is that the more stable this anion or this conjugate base is, the stronger your acid will be, right? Because if you have your HA and it's forming H plus and A minus, if this guy here is very stable, like you've got a very electronegative element, or it's something that's very, very big, or there's some resonance or something else that can help balance out this negative charge, it's going to make you a much stronger acid. All right, so now we're going to look at some specific cases of applying this kind of thing. All right, so if you have a binary acid, so this means you've got hydrogen and only one other element. All right, so binary, right? So you got if you're looking within a group, that HA bond strength is generally the most important factor. All right, so the weaker the bond, remember, the stronger the acid. So if we're looking down a group, remember group is up and down. So if we're looking down here, HF has a fairly strong bond, and that's because these guys are very, very close together. So even though fluorine is the most electronegative, because this bond is fairly strong, it's the weakest of these acids. All right, and then hydrochloric acid is slightly weaker than hydrobromic acid. And then we can and it follows the same thing as we go across here, as we look at water and hydrosulfuric acid, and then hydrosalinic acid. You can see that the acidity increases as we go down because that bond is getting weaker as we go down. All right, and then ammonia versus whatever pH3's fancy name is, you can see that that it goes from a weak base to a very, very weak base. 4 times 10 to the minus 28th. This acts like an acid much more easily. Anyway, and then if we're looking at it across a period, all right, the bond polarity is the most important. Okay, so the more polar that bond is, the stronger your acid's going to be. So if we look across here, our pH3 to our H2S, this is much more polar bond, so this guy will increase, or is much more acidic. And then between H2S and HCl, again, much more polar bond, so they increase. So generally, these are your trends: increasing acid strength to the right and increasing acid strength going down. All right, your oxyacids, all right, these are acids that consist of hydrogen, oxygen, and then one other element that is always a nonmetal. So this would be like your nitric acid, HNO3, or your sulfuric acid, H2SO4, or your phosphoric acid, H3PO4. Right, these are all your oxyacids. All right, generally the most important thing that helps these guys be more acidic is the electronegativity. All right, the more electronegative that nonmetal is, the acidity will increase. All right, and this is, specifically, you're looking for guys that have the exact same structure. So here you can see down here you've got your electronegativities of the thing that's attached to your hydroxide, your oxyanion here. And so you've got hypochlorous acid. So these guys all have the same structure. So you got ClOH, BrOH, IOH, and HOH. And so you're looking at this electronegativity. Chlorine is the most electronegative of the bunch, and it's got the highest Ka value of the bunch, so it's the most acidic. Hydrogen has the lowest electronegativity of the bunch, and so it's got the lowest electronegativity, and because that's water, it happens to be equal to Kw. Right. Now, if your oxyacid is with the same other element, okay, it's like, so if an element can form more than one oxyacid, the one that has the most oxygen atoms is the most acidic. All right, so for example, sulfuric acid versus sulfurous acid. Remember, sulfuric acid would be H2SO4, and then sulfurous acid would be H2SO3. Okay, so it's essentially if the oxidation number increases, the acidity increases. So remember how to calculate the oxidation number. You're taking the bonds that it's the number of electrons that it came with minus the electrons that it currently has. So here's your hypochlorous acid. All right, it's only got one oxygen attached here, and then chlorous acid slightly stronger. Chloric acid is one of our strong acids, and perchloric acid is one of our strong acids. So our acids increase as we're adding these oxygens, all right, to it. Carboxylic acids, last one here. Our carboxylic acids are organic acids, and they contain this COOH group, so like acetic acid. All right, so here's acetic acid that they've drawn down here, and the most important factor that's affecting this is, it's got obviously a pretty good polarity because this carbon, oxygen, or this hydrogen that would be attached here. But most important is that the conjugate base of this guy has resonance. So you can see here as we go from this guy here to this one that this negative charge can flip, right? It can be on this oxygen, or we could redraw it so this electron moves here, and then this bond can move up here. And so when that occurs, you get the double bond here, and now the negative charge is up here on this oxygen. Remember, whenever we have anything in resonance, it's not existing as this and then flipping over here to this one on the right and then back to the left. It's really existing as both of them together, and you're getting that hybrid structure. So really, if we were going to draw the hybrid structure for acetic acid, right, correctly, it would look something like this, with the carbon, and you have your oxygen and your oxygen, and then you have a partial positive or double bonds here and here, and then you have this partial negative kind of thing going on, where that negative charge is shared between both of those. And because it's being shared, instead of locating just at one oxygen, it's much more stable of an anion. All right, so we can use resonance to help stabilize that anion. All right, so anyway, so the whole goal of this is that you can use these kind of general guidelines that if given a group of acids, you can narrow down and help yourself figure out, well, what exactly is going on here, which one's going to be the strongest acid, just looking purely at its structure. All right, so anyway, do practice problems. Let me know if you have any questions, and I'll see you on the flip side.